So, we had derived the transformation equations for electric field and magnetic field as one goes from one inertial frame to the other inertial frame. And then we also worked out a problem where a charge is moving with a constant velocity v, and because of that we had written expressions for electric field. And today is the turn of magnetic field. We would like to write the magnetic field due to this moving charge. So, the transformation equations are here on the board. These are the transformation equations going from S to S prime, and in our scheme we will go from S prime to S. Remember, what we had done is we have taken a particle, this is S prime, and a particle moves with velocity v, and at certain instant it is at the origin, and at this instant we are writing what is the electric field, what is the magnetic field at this point x y 0. And our scheme was that we set up S prime frame which is also at this origin of S prime is at this point at t equal to t prime equal to 0 when this particle is here. So, that I take as t equal to 0, t prime is equal to 0. So, S prime is here, and after that q moves with velocity v, S prime moves with velocity v. So, this q is always at the origin of S prime, and hence if I look at this whole situation from S prime, what I feel is very simple situation. The charge q is placed at the origin, that is it, and therefore we know what is the electric field, what is the magnetic field here, and then from here to here we make the transformations. So, electric field we have already done and magnetic field we have to do. So, the magnetic field equations are here, Bx prime is equal to Bx and all that, and we will be using the inverse. So, let me write those equations first. So, it will be Bx equal to Bx prime, okay. Bx is equal to Bx prime. I am interchanging primed and unprimed symbols, and then V should be replaced by minus V. For here it will be By equal to, it will be By equal to By prime, this By is equal to By prime, and then this V becomes minus V. So, minus V by c square Ez, minus V by c square Ez, and this whole thing divided by square root of 1 minus V square by c square, and finally Bz equal to Bz prime plus V by c square and Ey prime and divided by square root 1 minus V square by c square, right. So, change V to minus V, and primed and unprimed symbols you have to change. So, these are the transformation equations. In this frame we have 0 B. So, Bx is equal to By equal to Bz is equal to 0, because the charge is at rest here. So, there is no magnetic field, and the electrostatic field, electric field we had written Ex prime, Ey prime and Ez prime. On the board I have Ey prime, expression for Ey prime I have here, Ez prime is anyway 0, Ex prime perhaps I do not need, so it is fine with me. So, let us start. Bx is 0 because Bx is Bx prime and Bx prime is 0. In this frame no magnetic field, so it is 0. By prime 0, Ez prime again 0, Ez prime again 0. So, By is also 0, so it is only Bz, and how much is Bz? Bz is Bz prime which is 0 plus V by c square. So, plus V by c square, here is V by c square, Ey prime, and Ey prime we had derived it in the previous lecture, it is still on the board. So, I will use this. This is Ey prime. So, it is q r sin theta, then 1 minus v square by c square power 3 by 2 divided by 4 pi epsilon naught r cube 1 minus v square by c square sin square theta and then to the power 3 by 2. This is Ey prime, v by c square into Ey prime, and that divided by square root 1 minus v square by c square. So, that divided by square root 1 minus v square by c square. So, this square root 1 minus v square by c square will cancel half power from the numerator here. So, you will be left with q into v into r, q into v into r, then sin theta, and this is 1 minus v square by c square divided by 4 pi q into v into r I have written. So, 4 pi epsilon naught c square and r cube, right, 1 minus v square by c square sin square theta and 3 by 2. Alright, once again check, q into v into r is here, then sin theta and 1 minus v square by c square, and then this c square is here 4 pi epsilon naught, 4 pi epsilon naught c square and then r cube and 1 minus v square by c square sin square theta 3 by 2. So, that is the magnetic field. We have gotten the expression of magnetic field. The magnetic field is in z direction, y component is 0, x component is 0, and you have z component only. So, it is in z direction. So, you can use your right hand thumb rule. If it is a current in this direction, you know, if you have a current in this direction, you can put your right hand thumb along the current and the fingers will give you the direction of magnetic field. So, here the magnetic field will be coming out of the board, and this is x axis and this is y axis. So, z axis in that direction. So, magnetic field for this current would have been in z direction. What we say is, you do not have a current as such, you do not have a wire, you do not have a linear charge everywhere here to large distances moving, it is one single particle. So, because of that also the magnetic field is in that same direction. It acts like a current element, it acts like a current element, and if you remember Biot-Savart law, because of a current element, if you have a current I and a small length dl, consider only this much, it is part of a bigger circuit. So, you have a current in a circuit, and from there I take just a small part of length dl, and because of this part, what is the field here? Okay. So, if this is r distance and this is theta, then the Biot-Savart law is that dB is equal to mu naught I dl cross r divided by 4 pi r cube. So, that is Biot-Savart law, and this 1 by epsilon naught c square, that you can write mu naught. So, you can put mu naught here. So, it is mu naught by 4 pi, mu naught by 4 pi r cube is also there, and dl cross r will be mu naught. So, if I take the magnitude, let me take the magnitude. So, let me take the magnitude. The magnitude is here is dB is equal to mu naught I dl and then r and sin theta, where theta is the angle between this dl direction and this r direction, and then divided by 4 pi r cube. So, this r you can cancel, it will be r square, here also r can be cancelled and it will be r square. So, that comes from the Biot-Savart law. But this charge moving, single charge, one single charge moving in one direction, can you call it a current element, and can you use Biot-Savart law? If I compare this with this, the expressions are very, very different. So, a single charge moving, for that Biot-Savart law as such cannot be applied. This is the real magnitude of magnetic field, and this comes from the Biot-Savart law. But if the speed of the charge is small as compared to the speed of light, if v is much smaller than c, then you can make some simplifications. Okay? Then you can make some simplifications. You can neglect this v square by c square here, and then it will be q into v into r sin theta divided by, here also it is v square by c square. So, you can neglect that in comparison to 1, and then it will be 4 pi epsilon naught c square. 1 by epsilon naught c square you can write as mu naught. So, it will be mu naught here and 4 pi here, r cube. That is all. And you can see that if you say that q into v is equivalent to I into dl, it matches. Q into ideal, mu naught into ideal, then mu naught into qv. So, for ideal, if you write as q times v and then r sin theta 4 pi r cube, it matches. So, a single charge moving with velocity v, q times v, that can be treated as your current element, and then you can use Biot-Savart law to get the magnetic field. But in general, no. In general, if v is not much smaller than c, then you should use this whole expression. Okay. So, that is about the electric field, magnetic field due to a point charge moving. Now, one more thing I would like to point out in this course is that electric field and magnetic field have these transformations that we have used, and we derived these transformation equations using Lorentz transformation, right. Remember how did we derive all those equations of Ex prime, Bx prime and all those equations, transformation equations? We started with a particular situation, and then we calculated force on that particle, electromagnetic force on that particle, q times E vector plus q v cross b, and we transformed that force from S prime to S or S to S prime, and from there we derived all these things, and force transformation is based on the Lorentz transformation. So, these are related through Lorentz transformation. So, we had several sets of quantities which are related through Lorentz transformation. We have that Ct and the space coordinate x, y, z, and they transform according to Lorentz transformation, and we say that it makes a 4 vector. So, let me write. So, it is Ct x, y, z, this is your position vector, 4 position vector. Now, this transforms according to the Lorentz transformation. If you write it in S prime frame, then this is your Lorentz transformation matrix, gamma minus beta gamma 0 0, then minus beta gamma gamma 0 0 0 0 1 0 and 0 0 0 1. This is that Lorentz transformation matrix, and here you write the components in S frame. So, Ct here, x here, y here, z here. So, this is a 4 vector, and all these 4 components in S frame and in S prime frame are connected through this. This is the Lorentz transformation matrix L. And anything, any 4 components, set of 4 components which transform according to this equation as you go from S to S prime is a vector, is a 4 vector. Here we have 6 components Ex, Ey, Ez, Bx, By, Bz. So, we cannot write this kind of equation, this is a 4 by 4 matrix. So, you cannot create just a vector out of those 6 components, but then there is another quantity or another class of quantity which we called second rank tensors. And these have 16 components. If my vector has 4 components, then this second rank tensor will have 4 square, that is 16 components, and this quantity itself will be represented by a 4 by 4 matrix. So, let me say A11, A12, A13, A14 like that, A21, A22, A23, A24, then A31, A32, A33, A34, A41, A42, A43, A44 like that. So, if you have a quantity which can be expressed in terms of such 16 components in a given frame, and if it so happens that in S prime you have these components and in S you have these components, corresponding components A11, A12 etc., A44 like that, and this is L here, remember this is L. If it so happens that this whole thing can be written as this L here and this L here, rather L transpose here, transpose means row becomes column, first row becomes first column, second row becomes second column and so on, that is called transpose. But this is a symmetric matrix, so even if you do the transpose it is same as L. So, you write this matrix here, you write this matrix here, and in between you write this 4 by 4 matrix of this quantity in S frame. So, these components are in S frame and these components are in S prime frame. So, any such quantity for which you have 16 components in a given frame and the components in S frame and the components in S prime frame are related by this relation 4 by 4 matrix, Lorentz transformation matrix here, Lorentz transformation matrix here, and in between this quantity, these components, such a quantity is known as second rank tensor. And it so happens that this Ex, Ey, Ez, Bx, By, Bz happen to be a second rank tensor components in some fashion. So, let me write what is that. We call it electromagnetic field tensor. And how do I write that? That is, let me write it here. The 16 components are created out of these 6 quantities Ex, Ey, Ez and Bx, By, Bz in the following fashion. All the diagonal elements of this are 0. So, 0 here, then 0 here, then 0 here and 0 here. And then you write Ex by C here. This component is Ex divided by C. This component is Ey divided by C. This component is Ez divided by C. So, the first row is complete. In the second row, you have Bz here, Bz, Z component of magnetic field, and you have minus by here. In the third row you have bx here. So, I have written half of this 4 by 4 matrix including this diagonal. So, these are your diagonal elements, and then the first row is 0, x component of electric field by C, y component of electric field by C, z component of electric by C. In the second row I will just write here, and the second second row and second column, this is 0 here, bz here, then minus by here. I will write the components here, but then in the third row third element is 0, then bx, and in the fourth I have written 0. To write the remaining components, you just reflect these things in the diagonal and change the sign. So, it is Ex by C here, you reflect, you get minus Ex by C here. You have Ey by C here, you get minus Ey by C here. You have Ez by C here, so you write minus Ez by C here. Similarly, come here. So, what is the reflection? The reflection is Bz here, so minus Bz here. So, this row is complete, this row is complete, this row is complete, this row is complete, and 2 elements are to be written here. When you reflect in the diagonal, this Bx will come here, becomes minus Bx, and then when you reflect on this, what you get is By. This is minus By, so the reflection is By. So, By. Okay. So, this is in S prime. So, you write prime 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 prime. So, from the 6 components Ex, Ey, Ez, Bx, By, Bz, we have created this 4 by 4 matrix, and I am using the components seen in S prime frame, that is why all these primes are there. In S prime, what are the components? Same components without prime. So, let me write that here. Let me write that here. Once again, it is 0 here, then it is 0 here, then it is 0 here and 0 here. Here you have Ex by C, then Ey by C, and then Ez by C here. Then you have Bz here, and this component is minus By, and then you have Bx here. So, that is this half, and then reflect. So, minus Ex by C, minus Ey by C, and minus Ez by C, and reflect. So, this component here is, this is Bz, so it is minus Bz here. This is Bx, so it is minus Bx here. It is minus By, so it is plus By here. So, these are the components in S frame. Now, it so happens that if you put this Lorentz transformation matrix here, and if you put this Lorentz transformation matrix here, the transpose is same as the original matrix, and then make a matrix multiplication, this 4 by 4 into this 4 by 4, you get a 4 by 4, multiply that by this 4 by 4, you will get this. And therefore, this electromagnetic field, one entity electromagnetic field, is a second rank tensor, transforms according to the laws of the second rank tensor. The Lorentz transformation is involved. Is the Lorentz transformation same matrix gamma minus beta gamma 0 0, it is this matrix which you write there, which you write here, and from that matrix multiplication you get the primed components in S prime frame. So, that is about this electromagnetic field. You can write all Maxwell's equations in terms of this tensor. It is a separate electrodynamics topic, I am not going into that, but yes, the components do transform according to the Lorentz transformation, but not like a vector, like a second rank tensor. So, I have covered the main topics in special theory of relativity. I would love to give some lectures on geometrical representations of this Lorentz transformation and derived equations. and it is all because of all due to a professor, Einstein's professor, mathematics professor Hermann Minkowski, and he was a mathematics professor. Einstein was a student in his class, and somehow when published paper, Einstein published this paper in 1905 of special theory of relativity. After that, this Minkowski developed a geometrical representation of all those Lorentz transformation and length contraction and time dilation and relativity of simultaneity, this, that, and many more things. And that paper was published in some 1908 or so. It is a beautiful representation. It is all geometry. What they do? They take time and space as one entity. If you, for space, if you just take x axis, your particle is on x axis always. Most of the time we have done that, right? Most of the time we have done that. So, if your space is confined to only x axis, then this Minkowski's diagrams, which we call generally Minkowski's diagrams, in that you plot two axes, right here x and right here Ct. Then any event, some event has occurred at certain location at certain time. So, what is the location? Location is some x. What is the time? Some time t. So, you can plot a point here. So, an event which is occurring in space at a certain time is correspondingly represented by a point. So, that is the whole game, and just on this he has constructed a beautiful geometrical representation which can be taken as alternative formulation of special theory of relativity. So, I would give some 2 or 3 lectures on that, and that will be the last part of the course.